Hello everyone. In this video, I'm going to find the solution to the governing differential equation of a single degrees of freedom damped vibrator system. If you have not watched part 1 of the video in which I have derived the governing differential equation of a single degrees of freedom damped vibrator system, I highly recommend that you go back and watch the part 1 of this video before we actually find the solution to the governing differential equation. Now, if you're already conversant with the governing differential equation, then you may actually want to find how to, you may actually want to check how to find the solution to the governing differential equation. So here we go. First, let me write the governing differential equation. We have m into d square x over dt square. That is mass times acceleration. That is the inertia force, plus c into dx over dt. Okay, that is damping coefficient into velocity, so that is our damping force. So these two are inertia forces, plus k, which is spring constant, times x is equal to 0. What this equation actually is telling us, well, the sum of algebraic sum of all the forces, the net resultant, the net force is going to be 0. Okay, so that is the meaning of this particular governing differential equation. I used to say that every governing differential equation has a secret that is stashed inside the governing differential equation. So this is the secret. Now you can call that as dependent variable if you wish, but I think I would fancy the idea of calling that a secret, because when you solve the governing differential equation, you actually get the secret out. So I used to call that a secret. That actually develops our temperamental proclivity towards solving the governing differential equation. Okay. Now, to solve this governing differential equation, we have to assume a solution. We have to guess the solution. So let us make an educated guess. The solution that we are going to guess is x is equal to a, which stands for the amplitude, into e raised to the power lambda t. Now immediately you may ask me this question: how do we say that the solution is x into a into e raised to the power lambda t? I'm going to give you the reasons why we are going to assume this solution. Before we actually solve the differential equation, I'm going to give you the reasons why we actually assume this particular solution to this second order differential equation. The first thing that you have to notice is, if you differentiate e power lambda t, or e power t for that matter, let us make it simple. If you differentiate e raised to the power t, whether you differentiate it one time, you are going to get the same. If you differentiate it 2 times, you are actually going to get the same. If you differentiate it n number of times, it's not x raised to the power n, but what you are actually trying to do is, if you differentiate any number of times, right, even 3 times, 4 times, so on and so forth, you are still actually going to get e power t. And this is very convenient for us, because here there is 2 times differentiation. You see, we have to differentiate it 2 times here. We have to differentiate it 1 times here. Well, we just have to substitute the value of x here. So conveniently, in every terms, you are going to get e power lambda t, because you will be differentiating e power lambda t. You are actually going to get e power lambda t. Of course, you will be taking lambda outside, but that's a different story. But you will be getting e power lambda t. That's my point. And if you are getting e power lambda t in every term, you can get e power lambda t outside. And right hand side, you see 0. You can easily throw e power lambda t on the right hand side. So it vanishes like a puff of a sand. It just vanishes. When it is vanishing, it means that it becomes very convenient, conducive for you to solve the equation easily. Okay, this is just a mathematical explanation. But I also have to give you other explanations. That is, this e power lambda t, it is going to capture all possible types of solution. Let us see what are the various types of solutions. Suppose you are plotting x along the y-axis and a time period along the x-axis. Remember what x is. It is the displacement of the mass at any instant of time. So here is our system. You have a spring mass damper system. So this is our spring. This is our damper. And you have a mass. It's a spring mass damper system. And see, because of this damper, this mass is not going to oscillate forever. Okay? The oscillation is eventually going to die down. Now, how do you think this oscillation is going to die down? Maybe this oscillation is going to die down in a sinusoidal manner, which means that the amplitude keeps on decreasing over the period of time. So the amplitude of oscillation may die down in this manner. Okay? So this is one possible type of solution. There is another possible type of solution where the amplitude may die down a little slowly, right? Like this. Not as slow as the oscillation, but you can see there is no oscillation in this case. You see, it's just dying down. There is no oscillation. This is also a possible type of solution. Or maybe the amplitude is going to die down at the shortest time possible. Okay, the shortest time possible. Okay, maybe I should have started the oscillation from here. Right. Okay, anyway, you were all able to understand the concepts here. Yes. So you can see that maybe the oscillation is going to die down. That is case 1. That is shown by the green color here. Or maybe the oscillation is, there is no oscillation, but it takes some time before it settles down to the equilibrium position. Or maybe the mass is going to go back to the equilibrium position at the shortest span of time. And this solution, x is equal to a into e raised to the power lambda t, I'm putting a box here, is going to capture all of these solutions, whether it is going to, the oscillation is going to die down exponentially, right? Or maybe it is going to follow the white path. Well, this solution can capture that. Or it is going to die down very quickly in the shortest span of time, the one that is shown by red in color. Well, it can also capture that. So you have a very good reason why you have to assume a into e power lambda t. Okay, so that is clear. Now, there can be another explanation. You may ask me this question, why not assume x is equal to a into cos lambda t? Why don't you assume this solution, a trigonometric solution, or maybe x is equal to a into sine lambda t? Well, you can also assume this type of solutions, right? Trigonometric solutions. Why don't we start assuming solutions like this and start feeding the x dash, 1 times differentiation, x double dash, and all the values in this particular differential equation. If we start feeding all these values in this differential equation, then what do you think you are actually going to get if you start feeding this equation? Well, you can see, obviously, if you differentiate it 1 times, you are going to end up with cos term. If you differentiate it 2 times, you are going to end up with sine term. So definitely you are going to end up with cos terms and sine terms. There will be cos terms and sine terms in the differential equation if you feed the values. If you feed the differentiated values in the governing differential equation, then you are actually going to get these values in terms of sines and cos. Well, you don't have a common term. If you don't have a common term, you cannot take them outside. If you cannot take them outside, you cannot throw them on the right hand side. It cannot become 0. So the equations are going to get a little bit complex. Okay. So that is the reason why we cannot assume a trigonometric solution. Well, let us try to assume a polynomial solution. You may ask me, why not assume a polynomial equation? Say, for example, x is equal to a naught plus a1x plus a2x square plus a3x cube. I have to assume a solution that is differentiable 2 times. Okay, so if you want to assume a3x cube, or if you don't want to, but anyway, if you're assuming a solution that is differentiable 2 times, of course this is a solution that is differentiable 2 times. If you're assuming solutions like this, then you have to find out the values of the constants a0, a1 and a2. Again, this is a polynomial equation, right? Hardly it can capture the oscillations. And again, you have to find the coefficients a0, a1, a2. So there is a very good chance that your equations may get twisted around. So it's not very convenient or conducive to assume a polynomial equation, because if you see, in the case of a into e power lambda t, you just have only one coefficient, maybe lambda, that you have to find out. But here you have to find out a0, a1, a2. You can apply the initial boundary conditions, but this is not a very good solution. You see, it's not going to be a very good solution, because it is not going to capture the oscillations over the period of time. Okay, it's okay. So this is the explanation for why we are actually assuming a solution of this particular form, a into e raised to the power lambda t. Okay, let us continue solving this governing differential equation. So let me write the governing differential equation again. We have the inertia force m into d square x over dt square. This is one of the reactions. You have the reaction that is provided by the damper c into dx over dt, and you have an action force which is kx, and the sum should be equal to 0. Remember, this is the case only when the spring is pulling. When the spring is going to offer the resistance, the momentum, the rate of change of momentum is going to be the action, and the damping and the spring will offer the reaction. So either way it works out. Okay. Now the solution that we are going to assume is x is equal to a into e raised to the power lambda t. So this is the solution that we have assumed. So let me first differentiate this equation 1 times. So dx over dt. So the value of dx over dt is a into e power lambda t. If you differentiate, you are going to get e power lambda t. Of course, you will be getting this lambda common outside. Let me differentiate this equation again. D square x over dt square. If you differentiate this equation 1 more times, you'll be getting a and different into lambda into e power lambda t. If you differentiate, you are going to get e power lambda t. Again, differentiation of lambda t is lambda, so that should be thrown outside. So that becomes lambda into lambda, that is lambda square. So let us feed the values in the governing differential equation. So if you just feed the values in the governing differential equation, then maybe I can use the space on the right hand side. Okay, so if you start feeding the values, it is going to be m into d square x over dt square, which is a into lambda square into e raised to the power lambda t, plus c into dx over dt, which is going to be a into lambda into e power lambda t, plus k into the value of x is e power lambda t, and that is equal to 0. So the common term here is e power lambda t. You can take them outside and throw it on the right hand side, or you divide the left hand side and the right hand side by e power lambda t, so you get rid of e power lambda t. So the equation that you are going to get after getting rid of e power lambda t is m, okay, I think I forgot the a, so you're also going to get rid of a. Okay, so after getting rid of a into e power lambda t, the equation that you are going to get is m into lambda square plus c into lambda plus k is equal to 0. So this is a quadratic equation. You know how to find the quadratic equation. Solve a quadratic equation. We are just going to solve the quadratic equation. This is of the form ax square plus bx plus c is equal to 0. So if you want to find the value of x, it is minus b plus or minus root of b square minus 4ac divided by 2a. So use that formula to solve the quadratic equation. It is minus b, the c is in place of b, plus or minus root of b square, which is c square, minus 4ac, which is 4 into m into k, whole divided by 2a, which is 2m. Okay, that's our solution for lambda, but let us simplify this even further. So let me bring this guy over here. Okay, so lambda, okay, here we go. Lambda is equal to, let me divide by 2m for each of these terms, c by 2m plus or minus. Can I bring this 2m inside the root in the denominator? If I bring it inside the root, I should be getting 4m square, right? That's right. So if you bring 2m inside the root, it's 4m square. So hope that is not confusing. Maybe I can write it here. So root of 4m square is nothing but 2m. So 2m can be written as root of 4m square, which means you can nicely bring that inside the root. So you'll be getting c by 2m whole square. So in the denominator, you are actually, if you take the square, it's 4m square inside the root. If you take it outside the root, it's just 2m. And here, if you just take it inside the root, 4mk divided by, it is 4m square. 4m square. That's it. So what I have done in this step is take this 2m inside the root, put it in the denominator. So that's what I have done. So lambda is equal to minus c, okay, divided by 2m. Let me simplify the terms on this side, plus or minus root of c by 2m, okay, the whole square. And the 4 cancels each other out. 1m here and 1m in the numerator cancel each other out. So you'll be left out with k by m. Now, what I'm going to do in this step in a moment is I'm going to multiply and divide by omega n. Okay, so if I multiply and divide by omega n, which is natural frequency of the system without a damper, keep that in mind. I'm not going to do any damage to this equation. I'm going to multiply and divide by omega n here, right? If I multiply and divide by omega n, I'm not going to do any damage to the equation, so that is clear. And also remember, the equation for natural frequency omega n is root over k by m. Okay? If that is the case, then omega n square is k over m. So this term can be replaced by omega n square. Remember, natural frequency is a property of geometry and material, right? Because stiffness is a property of geometry and material. Of course, natural frequency is also depending on the mass. Now, what I have done is I have conveniently represented everything in terms of omega n. Okay, so let me do the next step without any further confusion. We are going to do the next step. Okay, here we go. Let me write the next step for clarity. So lambda is equal to, so what is that we have got? Lambda is equal to, it is minus c into omega n divided by 2m omega n. Minus c into omega n divided by 2m omega n, plus or minus inside the root, it is c into omega n divided by 2m omega n whole squared. C into omega n divided by 2m omega n the whole square, that's right, minus, now k by n is simply omega n square, that's right. Now I will simply say, I say for example, let us bother about the physical meaning later. I'm just going to say let c suffix c is equal to 2m omega n. It is called as critical damping coefficient. Why it is called as critical damping coefficient, we will see that in a minute. But if you do that way, then the denominator, this term, can be replaced by c suffix c, and this term can be replaced by c suffix c. So we call that as critical damping coefficient because what happens when c suffix c, the denominator becomes equal to the numerator? That's the question, okay? It's fine. It is called as c suffix c, okay? And I'm going to do one more change, that is bring this omega n outside the root. So let us do it. So here we go. Lambda is equal to minus c by cc into omega n plus or minus square root of c by cc the whole square minus 1, because I'm going to take this omega n outside the root. That's right. Okay, outside the root. Now I can take omega n from this term and omega n from this term, take it outside as common, and I'm going to introduce one more term. Okay, so I'm going to say let c by cc is equal to, I don't know how to pronounce the symbol. Maybe some people call it as eta, some people are pronouncing this as psi, but I will go with eta. So let us say it is eta, okay? So what happens to the lambda now? So lambda is equal to minus eta times omega n plus or minus root of eta square minus 1 into omega n. Well, if you want, you can take this omega n common outside. So I should have done that in the previous step. I'm sorry. Minus eta into plus or minus root of eta square minus 1 into omega n. I'll put a nice box now. So that is our solution for lambda. Remember, you have two values of lambda. Okay? Initially, you start off the solution by assuming that there is just one value of lambda, but now you have two values of lambda. So what do? You want to find a general solution. So what do? The general solution can be you add the two values of lambda. Or maybe you should have started off with an even more general solution like a1 e power lambda 1t plus a2 e power lambda 2t. That also satisfies the governing differential equation. That will also serve the purpose. So now you are ending up with two values of lambda. So I want to aim at a very general solution. So I will say it is x is a1 into e power lambda 1t plus a2 into e power lambda 2t. Because I have two values of lambda, I am adding the two. And also note that this solution will also satisfy the governing differential equation. So we have a very good reason why we have to do this way. And assuming that there are separate values of associated values of amplitudes for each of the exponential terms. Okay. So this is a very general solution that satisfies the differential equation. Now let us substitute the value of lambda. So x is equal to a1 into e raised to the power. It is minus eta plus root of eta square minus 1 into omega n into t plus a2 into e raised to the power minus eta minus root of eta square minus 1 into omega n into t. All I have done is substitute the values of lambda. So I'm going to put a box. So this is our general solution to the single degrees of freedom damped vibratory system, this is our general solution. Now, remember, let us recapitulate the concepts. What is eta, by the way? It is C by Cc. And what is Cc? It is 2m omega n. And what is C? It is damping coefficient. It's the property of the damper. So you don't have any discretion about the property of the damper. You just have to choose the right damper. If you tune the values of m and omega n by changing the material and the geometry and the mass, so that when the value of psi can take different values. Well, psi can be greater than 1 if the denominator is going to be less than the damping coefficient. Then our equation is perfect. Well, when psi becomes equal to 1, then something strange is going to happen, because when psi becomes equal to 1, then this term is going to become 0, and this term is also going to become 0. You are going to get a different solution. You will also have to feed the values of psi is equal to 1. When psi becomes less than 1, see, something intriguing is actually happening. Something interesting is happening. See, when psi becomes less than 1, then the square of something that is less than 1 is always going to be less than 1. So this term here is going to have negative term inside the root. When you have negative term inside the root, you will be getting complex number. If you have negative term inside the root, you will be ending up with complex numbers. So there are 3 solutions possible depending on the various values of, did I call that a psi? Well, I'm using the word psi and eta interchangeably. Well, for 3 solutions for different values of eta, when eta becomes greater than 1, no problem. Whatever solution that I have put a box here, the red box, you can use that solution. When eta becomes equal to 1, well, then the term becomes 0. Root of the term inside the root becomes 0. So you are actually going to get a very simple solution. We will also see that. When eta becomes less than 1, then you are actually going to end up with a complex number. Now, these 3 solutions we are going to see in the next part. And we are going to use MATLAB to plot the solutions and to see how the solution for each of these 3 cases, how it would look like, and how it can enable us to take some smart, insightful, actionable, interpretable engineering decisions we can take from this. So thank you all for your patience. Thank you so much.